Now, we have tried and explained why the mass, how the mass reaches the core. But we would want to know what is the nature of the mass once it crosses the event horizon, or maybe inside the accretion disk. Is it in sizes of mountains or small pebbles or molecular in nature? So let us try and see what kind of mass size that we have. As we know, the accretion disk, the temperature that exists in accretion disk is in tens of thousands of degrees or tens of thousands of degree kelvins. So what would happen to any kind of mass which is existing in such an atmosphere? An atmosphere which has temperature as high as this. You pick up any element from the periodic table. You pick up tungsten, which is the mightiest element of the periodic table that we know of. The boiling point of tungsten is around 5,500 degrees centigrade. So even tungsten would evaporate in the atmosphere of accretion disk. Not just evaporate, it would possibly in plasma condition. So we know for sure that it is not in the sizes of mountains or pebbles. Obviously, it is molecular in nature. But is the black hole strong enough to pull apart the protons and the neutrons, or to split the atom, so to say? So for that, let us try and see what is the kind of gravitational force that a black hole has. And let us try and compare it with how much equivalent gravitational force is required to pull out a proton or a neutron of an atom. The biggest black hole that is there in the universe that we have come across is 30 billion solar masses. They are basically classified into the solar mass. One solar mass is the mass of our sun. So you put 30 billion of those, and that is the kind of black hole that is there. This is the worst or the biggest black hole that is possible. Why we are taking that condition is the extreme condition. So if that black hole cannot split the atoms, nobody else can. So what is the solar mass equivalent of G? Our sun, which is one solar mass, generates a gravitational force of 1.6 to the power into 10 to the power 12 G. And the fact that it is 30 billion solar masses, this comes up to 5 into 10 to the power 22 G. And what is the strong nuclear force which is binding the proton in the atom, a neutron in the atom? In the sense, if you want to remove it, you need to be exactly equal or beyond more than the binding force of the neutron and the proton. This is 100 trillion Gs. This works out around 10 to the power 38 G. So when you compare these two forces that the black hole can exert and the forces which are holding the proton and neutron together, the black hole, the biggest of black hole, is unable to split these atoms. So when you go across that plane, across the event horizon, and you have seen the mass which is swirling around, that mass is a soup of atoms, but it is not, how should I say, proton, neutron, quarks, or no, it is still in atomic nature. So another corollary that we want to, because what we are trying to do is how things are inside a black hole. So generally it is asked, all the black hole, the lights for the age of the black hole is falling into the black hole. So is it bright enough inside when you look around, when you enter across the event horizon, or is it pitch dark? So let us assume that there are three masses. You are this mass. There is one mass ahead of you, one mass behind you. And obviously you are not moving radially. You are moving concentrically in this vortex. So obviously the mass which is in front of you is traveling faster than you, and the mass which is behind you is traveling at a speed which is lesser. So you won't crash into each other, but for sure you are following each other. Now, would you be able to see the mass in front of you? If you are able to see the mass in front of you, which means the light which is falling on this is getting reflected and coming to you, then only you can see it. But when you say that the light is reflected and coming back to you, which would mean that the light is trying to escape from black hole, which is not possible. So the light falls on it, but it would not get received by you. So you would not be able to see the mass in front of you. So if you hold your hand, you won't be able to see your hand. So what happens to the mass which is behind? So what happens to the mass which is behind is, first of all, you are eclipsed. So if there is a light which is falling on this mass, it won't be able to reach you, because the mass itself, the mass behind itself, is stopping you from receiving it. There is a possibility that there is black hole, sorry, a light inside the black hole which is falling on this may get reflected to you. In that case, again, a light which has to fall on this surface which is behind you would again mean that black hole is the light is trying to escape from black hole, which is not possible. So in a way, you won't be able to see the mass either in the front or at the back. Only possible thing is when you're looking at the back, one may ask, what about the light which is coming from the left or the right of the place that you're in? But the problem here is the time zone. You are in one particular time zone, let us say T1, T2. The ones which are near the core is in T3, another one which is away from the core is in T1. These lights cannot cross the time zones. They don't have the time machine. So the light cannot come from the sideways. Possibility is that the light which is directly falling on your eyes, and if your speed is less than the speed of light, you will be able to see just that particular beam of light which is falling on you. So otherwise, inside, it's all